So you guys have a very pedestrian idea of density because it's been founded by what you just did in chemistry for the most part. So the way you calculated density, like you said, was mass per unit volume. But there's lots of different densities out there. Density is about a measure or a comparison of one thing versus another. So you can have population density, how many people live in a certain area. You can have, in this case, versions of mass density. In E&M, we talk about charge density and current density. A density is just how much stuff is packed into a certain space. But for us, we're dealing with physical objects. So we're going to have mass density as something we're going to be looking at. And there's three different kinds of mass density that I want you to know. There's linear mass density. There's surface density. And then there's volumetric density. Volumetric density is the one that you guys already know, mass per unit volume. But these other two, you should know, but you don't. But they're pretty obvious. For example, surface density is going to be mass per unit area. So you buy paper like this. Paper comes in thicknesses and densities, so you can get nicer paper. It's got a heavier count, or so much they measure it in pounds, but it's a mass per unit area. So cardstock is going to have a higher surface density than, say, typing paper or copy paper. The cheaper the paper, generally the thinner it is, or even tissue paper, which is extremely thin. I have a bunch of people that are in orchestra in the room. They should know all about the next one. Linear density is mass per unit length. That's how you buy the strings. Right? The ones that play the low notes, those are thicker. The ones that play the high notes, those are thinner. They have different mass per unit length. That's a different density. And there's symbols that go along with this. We use lambda for linear density and sigma, which is just an O with a little hat on it, for surface density, and volumetric density gets rho. So Greek letters again, but lambda, sigma, and rho are the symbols used for each. In the work we're going to be doing, a lot of what I'm going to expect you to do is take a look at an object and decide which kind of density works best for the object. And for the objects we're going to look at today and for the rest of the week, well, for Monday and Tuesday, our objects are going to have uniform mass density, which means that no matter which part of the object you take a look at, the density of the object at any part of the object will be the same as in any other part of the object. Now, you do understand that there's a lot of objects out there that have non-uniform mass density, which means the density isn't the same within the object. So there's reasons to study non-uniform mass densities. If you're an astrophysicist, stars do not have a uniform mass density, yet they spin, so understanding their moment of inertia is a valuable tool. It's how we calculate things like the amount of energy released in a supernova, understanding how the change in the angular momentum occurs as a star collapses is part of that calculation. Knowing the moment of inertia makes a big difference, and stars have a non-uniform mass density, which means you can't just treat them as a solid sphere. You have to do something else in order to figure out what their moment of inertia is. So in a lot of ways, these surface densities and volume densities and linear densities, they can become complicated because they don't have to be uniform. But for us, we're going to deal with only uniform systems for the first couple of days that we do this. So the first object we're actually going to use, or we're going to do, is a rod spun about its end. And again, we kind of know the answers to all the ones we're going to do. This one is going to be 1/3 ml squared. That's a rod spun around its end. We want to prove that that's what the moment of inertia is. We did a practice on this last week. And in the practice, we started with an understanding that we could take our single object up and break it into lots of little pieces. And by adding up each piece's moment of inertia, we could get a picture of the whole. So if you'll remember on Friday, we broke this up into 10 individual pieces, all the same size. And we found that if you break it into 10 individual pieces, The moment of inertia was 0.3325 ml squared. Not quite a third. And the reason is because although we broke it up into 10 pieces, those weren't point masses. And part of each piece had its mass closer to the axis of rotation than the other side of the piece. So today, we want to close that gap. We want to take and say, what happens if we take our object and break it up into an infinite number of pieces? And that's going to be a little more challenging, and it's going to require that we calculate the moment of inertia using an integral. Now, for those of you who are studying calculus, you understand that integration is a process. You are mostly learning right now processes on how to take antiderivatives and then apply that to your integration materials. So you're generally being given an integrand, and you're using whatever particular tool you're learning at the time to find the antiderivative. Would that be a pretty good description of what's happening right now in calculus? You're not formulating the integrand. So I'll be really clear. The hardest part about finding a moment of inertia isn't the calculus part. The hardest part is forming the integrand. That's going to be the part that's going to be challenging. We're going to break that into several steps to help you form the integrand. But ultimately, the integrand has two things that you're going to need to do. You need to find a way of expressing dm, which is a piece of the object's mass, in terms of the object's shape. That's the first thing we're going to do. Express dm, which is a piece of the object's mass. We're going to express that in terms of the object's shape. The second thing we have to do, we have to find a way of describing the distance from the axis of rotation to each piece of object. That's what r stands for. R is not radius. R is the distance from the axis of rotation to each individual piece of the object. So we're going to break this up into a series of steps, and they're going to have categories. So our first step is an overview. We're going to take a look at our shape, identify where the axis of rotation is, and decide which kind of density is the best one to use for this shape. You're looking for some kind of symmetry. You're also looking for what the shape of the object tells you about how it's shaped or how it's defined. For example, this object has very little by way of difference top to bottom, right? Each piece is going to have the same width top to bottom, which means if I take and break this object up into a piece, they're all going to be the same width from here to here. Do you guys agree with that? So I'm noticing that this object is very long compared to its other measurements, which makes me think the best kind of density to use here would be linear density, because it looks mostly like it is something very long. If you had something that was like a disk, I probably would use surface density, because it looks more like something that's two-dimensional. If you have something that's very three-dimensional, you might want to use volumetric density, but you choose a density that fits with the, in this case, the symmetry of the object. This object has some symmetry. Now, before you guys, kind of just zone out, thinking this is not that big a deal, this object has a lot of the same kind of features as the one we're working with, but obviously this object doesn't have the same density from the inside to the outside, right? It's getting smaller. It's not of uniform shape. So although I'm saying this one we can use linear density, we probably can't use linear density here, because this object's getting smaller as you work from one end to the edge. And to be quite frank, both of these have been on the exam before. So in choosing which type of shape you want to use and which kind of density you're going to use, you're kind of establishing for yourself how you're going to deal with the shape of the object. So I'm going to use that linear density. And the first thing I'm going to do is I'm going to express the object's shape and size using my linear density. I'm going to say the linear density of this object is the mass of the rod divided by the length of the rod. But that's the linear density of the object. All right, part two. Part one, again, just establishing what kind of density and what kind of things I can use to define my shape. Part two, you need to identify a piece of the object. What I mean is we are defining what one piece of the object looks like. This means to me finding a square of mass somewhere on the object and identifying it as an individual piece. Pick something somewhere in the object, because what you have to be able to do is you have to be able to find a way to use a coordinate system to point to that piece and define its size. So I identified a single square somewhere on the object. Now, once I've identified that square, I'm going to label it, because this square represents one piece of the object's mass. And therefore it has mass dm. dm stands for a piece of mass. So it's not much different than saying delta m, where delta m would be a part of an object. This dm takes that to the literal sense of an infinitesimally small piece. We're going to break this up into lots of these pieces. We're identifying one of them. Now, we will eventually have to convert this to something about the object's shape, and that's the whole deal, is figuring out how to write something about this object's shape. But our next step, after identifying that piece, is finding a way to point to that individual piece. We need to come up with a letter. Now, we're inventing characters we're going to use for integration only. These characters will not be in the final answer. They're for you to use in the process of integrating. This object's linear, so this is going to be super easy. I can point to that piece by saying that piece is this far away from the axis of rotation. And I'm just going to use x as a way of defining that piece. So I'm saying this random piece of object is a distance x away from the axis of rotation. Now, you should, before you go any further, figure out where the first piece would be and where the last piece would be, and can x be used to point to every individual piece. So I'm going to say the first piece is located at 0, right next to the axis of rotation. And the last piece is located at L, the piece that's furthest away. What I'm doing is creating the limits of my integration and figuring out what the range of x will have to be for this particular object. Since my object is linear, I only have one variable required to point to it. Two-dimensional objects will require 2 variables. Three-dimensional objects require 3 variables. So as long as you understand that one-dimensional objects only require 1 variable to point to them, you understand why you might want to reduce your objects to as few dimensions as possible. So you'll notice these pictures, the ring is, thin in that part, but thick this way. I probably would still want to treat this as a one-dimensional object if I could. Just taking my bar and bending it in a circle. If you can reduce the number of dimensions, you make your problems easier to solve. Now, we've pointed to the object. The next thing we have to do is define the shape of the object in terms of our pointer variables. So for this object, it's one-dimensional. I'm going to say that the shape of the object is a little bit more in the x direction. This was a 2-dimensional object, we'd have to define its area. If it was a 3-dimensional object, we have to define its volume. But because it's one-dimensional, we just have to define its length. Our object has a length of dx. So every piece of this object's mass is going to have a mass dm and a length dx. Once you have defined the object's size, you are ready to define dm in terms of its size. And this part's super easy. You're going to take the size of a piece and compare it, you're going to take the mass of the piece and compare it to its size, because this is the density of the piece. And you're going to set it equal to the density of the whole. So whatever type of density you've chosen, linear, surface, or volume, you take the density of the piece and you compare it to the density of the whole. Once you've done that, you solve for dm. So recapping part 2. Identify where the axis of rotation is and draw a square representing a piece of your mass. Define that piece as having mass dm. Create a pointer variable or variables that points to each piece of mass. Make sure your pointer variable has a range that gets you the first piece and the last piece. Define the size of the object using your pointer variable. Find the density of your piece and compare it to the density of the whole. Then solve that for dm. That was your series of steps that gets you to here. Part 3, you have to assemble your assemble your integration. So we're going to take our formula here and we're going to assemble the integral. This really has just 3 parts. First, replace dm with what you have now got as a way of representing the mass of the piece in terms of its shape. So our dm is going to be replaced with m over l dx. This is the density of the whole object times the length of the object, or length of the piece. Now we have to replace r squared with whatever pointer variables we're using that point from the axis of rotation to each piece. All right, this one's super simple because our object has linear symmetry. So each piece is a distance x away from the axis of rotation. So we're replacing r with x. And the reason isn't because r is a bad variable. It's because we want to have thought about how does each piece relate to the axis of rotation. For this one-dimensional object, this is super simple. But understand that they're going to get harder as we look at other shapes. The last thing you have to do is define where the first piece is and the last piece is. This is an integration. It takes information. And the way the integral symbol works is that you give it a range. You're doing a sum. We want to add up each piece from the first piece to the last piece. So you put the first piece at the bottom of your integration and the last piece at the top of your integration. These are called the limits of integration. All right, so that's ultimately everything necessary to calculate the moment of inertia, except for actually doing the calculus. And the calculus, I think, is going to be the easiest part for almost each of these. So if you guys who have had calculus, you understand that. But even you guys who haven't, we've done every form of calculus that you're going to need for this, because almost all of them are going to be polynomials. So this is an example of that. My expectation is that you remember how to do integration, or at least antiderivatives. So integration is a 2-part process. Part 1 is find the antiderivative, and part 2 is plug in your limits. That's all it is. It's the only difference between what we did first semester with antiderivatives and what we're doing now with integrals. So an integral has 2 parts, finding the antiderivative and then plugging in your limits. Now, for those of you who aren't in calculus, an integrand has the equation part and the part that tells you which variable is important. So right now, the variable that's important is x. It's our integrating variable. Any other variable is probably going to be a constant, unless it changes when x changes. For example, does the mass of the whole rod change when x changes? No, so m's a constant. It's not part of this. There was an m in every term when we did the summation. Do you remember how we pulled out all the m's? It's the same thing. We're going to pull out all the m's here. And does the length of the object change when we go from one piece to another piece? No, so m and l are both constants. They don't depend on x. So they can be pulled outside my integral. And what you will be left with is probably just the important variables. This says take the antiderivative with respect to x of x squared. Now, you have done this before, so you know about adding 1 to the exponent and dividing by the new exponent. So our first step here is just to find the antiderivative. Once you've found the antiderivative, you don't write the summation symbol anymore. So the integration symbol goes away, but you do have this bracket where you hang on the bracket your limits of integration as a reminder that you still have to put in your limits. That represents the next part. putting in your limits. So we're going to put in the limits now. That simply means putting in the upper boundary for x, subtracting and putting in the lower boundary for x. So putting in your limits, you put in the upper boundary for x, and you put in the lower boundary for x. And we're done. Simplify now. And I'm going to notice that there's an L cubed in the numerator and an L in the denominator, so I can clean that up. And I'll get 1/3 ml squared. Now, that's kind of what we expected here, 1/3 ml squared. A lot of work goes into doing that. But ultimately, the hardest part, and you may not believe me yet, but the hardest part is coming up with what to replace for your integrand. Now, you guys have seen this done. We have a few minutes. Can you redo it again? I want you to see if you can put a little bit of your mind into this. I want you to change the axis of rotation to be in the middle. And try it again. The answer is 1/12. You don't have to change very much, but maybe try going through that series of steps. Everything's going to be the same except for your limits of integration. Your limits are going to change because you're no longer going to have your axis of rotation at the end. You're going to change to have the axis of rotation in the middle. So this changes where you start and where you end. Try it. Try writing it out. We have 4 minutes left, or I'm sorry, 6 minutes left. I think we can do it. So does everybody realize that for the most part, you're not going to change dm for this? So we can almost jump to this step. Because nothing about the rod has changed. So it still has a mass m, a length L. We're still going to do the same thing for dm. We're going to have a small box that has width dx. We're going to still have dm over dx equals m over L. All of that's going to be the same. However, since we're starting with an axis that's in the middle, our starting box is going to be over here. That looks like it's negative L over 2 from where I am. And this one's going to be positive L over 2 from where I am. That's one way to do it. But also, remember, this is a summation. You're adding things. So do you notice that it's symmetrical? I can probably just say that I could start here at 0 and go over here to L over 2 and just double my answer, since I just have one on each side. Summations allow you to be a little flexible in how you do your integration. So you could either say, I'm going to go from negative L over 2 to positive L over 2. That's fine. That works. Or you could say, well, I'm going to go 2 times from 0 to L over 2. The same thing. I'm just using some of the symmetry. One of these is not better or worse than the other. However, sometimes with things like sine and cosine, you might find it better to do the half one and double your answer, because sometimes you get in trouble with the way sine and cosine works. Doesn't matter to me which one we do. I'll just do the top one, because what we're going to do now is the same thing we did before. We're going to pull out the things that are constant. We're going to do the antiderivative. Going to plug in my limits of integration. Everybody see that's all right? Just algebra now. 2 cubed is 8, right? Negative cubed is still negative times a negative is a positive, so positive 1/3 cubed over 8. 3 times 8 is 24. 1/24 and 1/24 is 1/12, right? It's 2 24ths, but isn't that 1/12? So m over L, 1/12, L cubed. I can cancel out an L here, I think. I get 1/12 mL squared. So all we really had to change there was our limits of integration. Now, tomorrow, ring about its center and the disk about its center. Both of those are pretty straightforward. We're going to do the disk one way, and then on Wednesday I'll show you a faster way to do the disk, one that's probably more likely to be what they would like you to do on the test. And then the rest of Wednesday we're going to look at what happens if it's not a uniform mass density, or if our shape isn't one of these shapes. We're going to do a triangle or something like that.